Okay, and I know I was rushing as usual, so I won't go out 5 minutes. Okay, so the thing that we covered for operators A or B or H. Oh, sorry. Let me use the book's notation. No, wait a minute. How did they do that? Oh God, what's wrong with me? I'm already gone off in a spiral. You see, I didn't have time. I didn't prep as much as normal. Obviously, I'm already gonna go off into never land here. How did I do that? So, like I was saying, I always complain about the book, and the book has this kind of. It's like this. It's A, T0, T. And then, of course, I need to do the graph the same way. Of course, I have to write it in reverse. Okay. So, obviously, these are time dependent. And A and H commute. B, A, or H do not commute. Does not change. Right, there's no time dependence to a state that is an eigenstate of the Hamiltonian. So of course that means is that A operating on this prime K ket gives you an eigenvalue. That's not important. What is important is this. So again, if the state is an eigenstate of the Hamiltonian, then this state, you know how to time evolve it. Time evolving it is hopefully for an eigenstate. This is a stupid joke, right? It's e to the minus Hamiltonian, which returns, of course, the eigenvalue of the Hamiltonian t, and we'll still use the book notation. Okay, so you talk about the non-time dependent quantum mechanics. What we've been doing, what you did for your undergrad, what we've been doing up until right now, here's how you time evolve it. E to the I Hamiltonian stuff times the state. And of course, the Hamiltonian just ends up sucking up its eigenvalue. So this is just a number, cosine of pi minus I sine of pi. It literally is that easy, something like that. And that's the time evolved state. Okay, the expectations for that state or that state don't change. Nothing happens. Nothing. Of course, that's cool. Now you know how to do time-dependent quantum mechanics, but nothing's happening, which is kind of funky. Now, I always thought, I just presumed that when we start solving wave functions, especially wave functions with Hamiltonians, that those are what the states are, that the molecules are in those states. And it turns out that that's now very questionable, because if so, nothing is happening. The universe is completely frozen. I mean, we don't even have temperature in a universe like that, because things couldn't move. Nothing dynamical is happening. So now we have a new problem. Like, what the heck makes things happen? Now that we've proven this. I know it's kind of funny. I mean, I just wonder, I'm obsessed with this idea. You know, this is a nice proof and it's not hard to work out, but now it engenders a question, why does anything move? Where does the dynamics of the universe come from? Okay, last time what we saw was, let me apply the Hamiltonian. I'm going to drop the T naught to, let's do our spin states, and remember that for the Hamiltonian being this is basically kind of like an EPR. For the Hamiltonian being, where is it? I'm in between my notes now, so I'm confused. minus I sz t over 2, right? This ends up being e to the right, because sz brings h bar over 2. No, sorry. There's the h bar, and then the h bar gets swapped out with the 2 because this is h bar over 2. The eigenvalue, the energy of that isn't it minus h bar over 2? No, it's plus h bar over 2. Okay, so that's right. Again, and I worked with some expectation values of this time evolving state, and I got nothing changing, right? I did some expectation values with it, and I just got the number 1 from examples of last time. And there's no t dependence to the number 1, which a 5th grader could see that. They wouldn't understand it, but they would know that there's no letter t. Okay, so again, we did some work with that, and it still doesn't involve the time, just like I said. Okay, here's another example. Okay, so let's, again, my arbitrary state. Let's make it, not some arbitrary state. We decided to work with Sx plus. And, of course, that is going to be e to the, let me remind myself before I go with that. Nice I plus normalization requires square root of 2 plus okay. Now we're going to work with a time evolving SZ plus, and the way we did that was, and this is very similar to EPR. In an EPR, you're working with electrons, right? EPR is like NMR except for unpaired electrons. It's identical. Magnetic field. The electrons spin. Remember, electrons like a spinning charge, and spinning charge have magnetic moments. It'll point up, it'll align itself with the external field. Okay, now just like 2D NMR, you know, the way 2D NMR works, i.e. the way all NMR works, when you're taking an NMR and you hit, I mean, a lot of you have done this, right? NMR, type ZG, it's like German or something, because those are Bruckers and those are German, and you see this oscillating signal. This oscillating signal is what I'm solving, by the way. But before you get that oscillating signal, what happens is it blasts it with some radio waves that turn the nuclear magnetic moment, or in an EPR, the electron's magnetic moment in the Fourier transform EPR, you turn it into the Sx plus direction. Right, you go from SC to Sx plus. Okay, so my point being here, to get some dynamics, we've pushed the system. Right, so here's one way to get dynamics, is to perturb the system. And there you go. Now we're going to see dynamics. And last time, I know I rushed on one thing. What did I do? I did, I've got to find my notes. Where am I at my notes? We're going to do something really more interesting today. And again, I hope this isn't like remotely difficult. You know, this is why I like, oh yeah, we did this. So what we did was we queried, we purposely put the thing in the SC plus state, and then we queried whether it stayed in that state over time. Right? We're seeing how well it overlaps its original self. And of course that ends up, now again, I'm sure I would have, you know, we have to have some kind of exam coming up. Let me write it down here. I should be able to throw something like this at you because you should think this is a joke, right? I'm going to write it a little bit differently just to save some room. Okay, so there's the bra, and unfortunately the time-dependent one is a little bit more complicated. It's what I just wrote, so I don't know why I'm writing it down again. Just to be exact. Of course, plus, when you FOIL it out, plus is okay. Minus is okay. Minus plus is not okay. That's 0. Okay, so again, middle school FOIL, except slightly easier. Thank you, Dirac notation. Just love that plus thing. And then let's take the absolute value of it, because that's what we always want. And as I mentioned last time, I'm repeating myself. Let me just get to the cut to the chase. You end up with e to the IWT plus e to the minus IWT, yada, yada, yada. Okay, so now I can do a quantum something something with the time operator and not get the number 1. Now I've got a t. Now there's time dependence. Right, and likewise, so I'm using the board often today, the expectation value, had we, what is this? Sorry, let me do this, x minus that ends up being sine. Okay. Had you done that, right? That just meant, just put a minus sign there. What happens is you have like cosine squared over 2 plus cosine squared over 2 and the plus I sine minus I sine. And then here, with the minus there, the opposite happens. The cosines will cancel and the sines will add together. Anyway, as a sanity check, cosine of 0 is what? Not hard to say. Is it 1? It's 1. Okay, so when I turn the thing in the x plus state, and I'm asking, is it in the x plus state at time 0? The answer is 1, which is yes. It is not in the sx minus state. No. Right? So all this makes sense. What it also implies, though, at some time later, at whenever this is pi halves, what is it? Anyway, whenever this is pi halves, I think. Yeah, pi halves. When enough time has passed such that w whatever time over 2 is pi halves, then that's 0, and then that's 1. So what has to be happening is the damn thing is rotating. Right, which is precession, and then it'll rotate back, of course. And by the way, in your NMR, now again, I'm technically been working with an electron, so I'm technically doing EPR, but it's identical. When you hit ZG, and you see that, that's what's happening. Technically the nucleus, not an electron, whatever, it doesn't matter. What's happening is the magnetism is spinning, and it's inside of a copper coil. A spinning magnetic, just like the spinning electric charge of the electron creates a magnetic field, a spinning magnetic field creates an electric charge, a moving electric charge, aka a current. That big, so the magnet is about 500,000, and that, you know, that electronics box that sits next to it, that's another 500,000. It's designed to amplify. It's an amplifier. That's almost entirely its job. Really sophisticated electronics to make sure that it gets that magnetism that's rotating inside of the coils and generating a current inside of the coils, and it's just magnifying that current using, like I say, very sophisticated electronics. Again, I'm still repeating what I did last time. And then the last bit, and again, I know I was rushing, you know, I always want to review anyway. And the last bit is, of course, you know, this would be a supreme, you know, one of the, I mentioned last time, I got confused sometimes when I see, you know, SX for being this, you know, when I look at the overlap of the inner product, sometimes I would confuse it for this, like they were the same thing. They're not, and of course what this is And I'll write the whole damn thing out. Now, I'm not going to do it because, again, I've really wasted a lot of time here. Here, I've got to think about it. This will be IWT because I'm doing a bra. So what I'm doing is the time on the left is the time evolving bra. Okay. Okay, SZ is, we've done it a bunch of times, it's not that bad. Remember that an operator can be put as like a linear combination of all of its states times the eigenvalue of that state. Of course, outer products are operators. Inner products are numbers, so that could not be the case. Oh God, this looks scary, doesn't it? Oh, now I gotta be careful. I gotta be careful I did this right. Minus plus, right? Remember complex conjugates, that'll get you. You know what's nice though is when I'm doing one of these problems, and usually, you know, week one I already know the answer, and I can see that like the sines and cosines aren't coming out. It's just because I missed a plus or a minus here. That's where I messed up. It's easy to figure out. As much as this is a lot, it's actually not that bad. I'm almost tempted to do it except really I'm out of time. Oh, wait a minute. Oh, this sucks. Oh my God, this sucks. Oh, what is that? No, it's not that bad. Right, it's not that bad. Actually, if I put that on your test, would you kill me? Yeah. Well, it's not that bad, right? Right, so SX plus in, see, I lost it there for a second because I'm using mixed basis sets. I'm using an SX basis set here, but I'm using an SZ basis set here. Yeah, in my notes, you know, when I was in grad school, I noticed that in my notes that our instructor did not actually do this problem, and I just assumed it was laziness. This is minus, right? No draw. Now I gotta look out for this. I know when I get obsessed. And I know I'll get it. It's just like, do I want to spend all day on this? All right, there we go. Okay. That's a lot, isn't it? But it's not, again, one of the things I also want to say to you, although I won't make you necessarily do it now, remember I told you the story that one of the TAs really got on my case when I was a new grad student saying, I complained about a problem like this. I said, oh, come on, this is too much. And this woman, she got in my face real hard. And I should find her and thank her. I'm sure I can find her. She said, if you want to be a PhD, you better be able to handle this kind of stuff. Yeah, she's right. And it's not even that bad. And what you end up with is, it ends up being, I think if you solve it this way, or you could actually, there's actually a couple of tricks. What you would find is that, depending on your approach, if you actually just put this as Sx evolving in time as opposed to converting it into the Z basis, you would actually get this. So I'm showing you, be careful here. What I'm showing you, by the way, is I'm showing you two ways to do this. So just heads up on that. So this is one way where you convert everything to the SC basis. I want to point out that I actually could have converted this to the SC basis. So two approaches. Convert the operator to the SC basis, or I could have converted this to the SX to SC. I could have converted SC to SX. You would have gotten this expression. And then you may notice that this is actually, I should have been more clear on that. Again, I should have probably spent a little bit more time gathering my wits together. Since I felt I had to run home and get that handout for you. Okay, and again, what you end up with is an expression that is actually incredibly simple. Again, we've started the system in the plus SX direction, and sure enough, the expectation value of SX at time 0 is h bar over 2. And likewise, maybe this is what I put on your test. Sy ends up, you go through all this rigmarole, and you find this. That 90 degrees out of phase is Sy, which makes sense because Sy is 90 degrees, literally 90 degrees turned from Sx, right? That comes out quite well. Again, sorry, I got kind of nutty there. You know, I shouldn't have gone off on this tangent. I should have actually just converted this into Sx plus, and it would have been a little bit easier. Anyway, so there you go. Alrighty, again, I spent way too much time on this. Like I say, maybe I'll put Sy on the exam. Of course, with enough, I'll break it into little parts so that you can follow along exactly how to derive it. Okay, now, I want to point out that the way you see time-dependent this or that in talks, they don't do it the way we just did. That's kind of nutty. What we've done is, as usual, a good introduction. The state is evolving in time, which makes a lot of sense, but let me show you how we really do it. And the book, I think, does an okay job of this. You know, it's a real mixed bag. So the previous stuff we've done is called Schrodinger Picture. Okay, it's called the Schrodinger Picture of quantum mechanics, where for some time, the expectation value of an operator over time is done by, and again, you should be rolling your eyes like, well yeah, we just did this. Right, where I time evolve the states, because why wouldn't I? Right? I'm just putting the key here. These are evolving in time. Okay, so boom. Now, how anyone ever thought to do this, or Heisenberg, kind of is a good name for a villain, right? Okay, watch this. Let me write all this jazz out again. Of course, the adjoint acts on the draw. Get this. Change that operator. And then don't let the states change. Just change the operator. Yeah? Hopefully right now you're thinking, okay, so what? All right. There's two things about this. For one, the book says like, oh, well, of course you like the Heisenberg picture better than the Schrodinger picture. And of course I'm like, what the hell are you talking about? The idea of a state evolving in time is inherently sensible to me. You know, the cat runs in circles. Of course it does. And when the cat's turned 90 degrees, it's looking the other way. It's the same cat, but whatever. And this looks like a math trick. It very much is a math. It's all math tricks, right? Okay. But it turns out that the reason the book keeps saying this is, and I'm going to jump ahead, and maybe you don't even have to write this down. Now I have to also stipulate this for a reason you'll see. For a free particle, because it matters. It matters whether we're talking about a harmonic oscillator, a spin, or a free particle. That's an EVIKX, right? That's no potential energy. Get this. Okay, when I say X operator with the 0, I mean it's just X. It's X. It's the same X we've been dealing with the whole time. And P is the same operator we've been dealing with the whole time, minus H bar derivative. Okay? Position in the future is the position now plus V times T. Right? Momentum is velocity over mass times velocity, so P over M is V. X plus VT is how things move. Okay, yeah. That's cool too. I've known about that for a while also. So I think they both have a lot of benefit. But again, when I was reading over the textbook and my notes and some other things, and they kept saying, oh, well, of course you prefer this. I'm like, what? And then later at the end you see this and you're like, oh, well, yeah, that's cool too. I mean, I like them both. Anyway, so I'm coming to the end there. All right, now how the heck does it work though? Okay, so what we're going to solve is called the Heisenberg equation of motion. Now it starts out, I have to admit, I'm kind of struggling to explain why we do this first step. Now we all know that U, of course, is e to the minus I h. And again, I'm going to get rid of that T naught 0. Okay, so the unitary time evolution operator is that it's not like, you know, we always know that we see these, the adjoints. It's just always like the complex conjugate. It's whatever makes you have to multiply them to get 1. Okay, so if this is position, then I just have these SOBs left and right. So, you know, what do you do? It turns out that that's kind of hard to work with. It's like, remember how I know you two have heard this a million times. If you're integrating a function, you know, if you integrate this, then you should look at that and say, well, that's pretty easy, right? Okay. The problem is I accidentally left this bit of information out. F is a function of x. Now it's, you don't know, I have to tell you what f of x is. This is the problem that we run into when it comes to this thing right here. That's just a motivation for why I'm about to do this. Okay. Okay, now it turns out, and let me also just tell you, I'm going to start writing things down from an approach that gives us the answer. Cool, right? And as for why I'm starting to write it down the way I'm going to write this down is like, what the hell? And there's not a lot I can do about that. Okay, what I'm going to do is I'm going to look at the time evolution of this operator. And often, all right, so what I'm going to try to do is I'm going to put time dependence to the operator so that you know that this is a Heisenberg operator. And if I'm doing a Schrodinger, you know, the normal operators, just x, then I'll still give it a parenthesis, but I'll make sure I just write 0. The book sometimes puts an S or an H. And even puts the little brackets with T or 0. It does both. It's a little overkill. And I'm afraid I may mess that up. Anyway, okay, so if you do this, it's not too hard. What you do is you do the product rule. EDT, here I should write this down. Of course, you know that the unitary operator has time in it. This operator doesn't have time in it. So that's our normal operator. So that's like X or whatever. Oh, it needs a hat. Okay, so time is only in the time-dependent operators, right? Remember, you haven't seen an operator with time in it up until, well, you still haven't seen a time. Oh, wait, okay, you just saw it for the first time. Okay. Normal operators. Okay. Now what you do is you do product rule. So you only see two things. Oh, sorry. Plus. Okay, then this guy, of course, is left alone because it doesn't have time in it. Here's the other function. So obviously this doesn't have time in it, so it's just, that's like a constant, right? So I took the derivative of the first function, and so now, of course, I take the derivative of the second function. And again, I will make sure to put a little 0 there, so no, so no time dependence. Okay. All right, next bit. Recall when we first looked at the incremental time evolution operator, 1 minus I Hamiltonian dt, blah, blah, blah. Okay, so I had to take a little bit of an aside here. You've seen this, so hopefully your head isn't going to, you're not going to get blown away. Remember I was telling you that this little formula with the time evolution operator is like the most crucial thing ever. Oh, and I need to make the parentheses bigger. There. Okay, that looks way better. Okay, so when I was talking about, when we introduced the time evolution operator, which increments stuff by dt, I said this is it, without much justification, and you should be able to derive this from the Schrodinger equation, because the Schrodinger equation can be derived from it. So it's a bit, remember I was telling you, that's like a bit of circular logic, I don't know how true that is. But if you're going to evolve a state to one time to another time, you just use the operator twice. That was the idea. And again, you've seen this before. So you see I've just taken the whatever, and I've added dt to it. An infinitely small incremental amount of time. Now you may recall that what we learned from this is, I'm not going to go through the whole derivation because I kind of blew up a lot of time already. If you bring this over, then it's this. It's this minus that is just an increment, is just an incremental change in the operator. And there's the I over h bar, rearranged a bit. Oops, that's impossible to do. Okay. So again, we've seen this before, so I hope this isn't blowing your head off. Obviously, what I'm going to do is I'm going to put that here. Now we could have also, you can of course time evolve a bra. You have to be real careful about complex conjugates or what's to the left, what's to the right. In this case, okay, complex conjugate, so I picked up a minus sign. And what's to the left, what's to the right. The adjoint will be to the left. Again, you always just, everything gets permuted. Everything's a complex conjugate. Flip all the operators. And you can just apply this on the adjoint to the left, and all of this comes out just fine. Right? That's how you time evolve the adjoint of an operator. Okay, we're almost done. And then an example, which is what is in that handout. I'll just set it up, and then you can look at the handout later, which, again, is not really, I don't think it's nearly as daunting as it looks. Okay, so that's my aside, so let's go back. Oops. The whole point is, okay, there's my, at the very top, right, so I'm at the top. Oh God, where am I at in my notes? Okay, so I'm doing the adjoint first, so, okay, so here, so that's why I picked up a minus IH bar. Oh, needs a hat. Oh, this isn't so bad. It gets bad here in 1 second. I'm gonna add a lot to it for like, oh, wait a minute. No, what have I done? I forgot the operator, Jesus. Yeah, right, that's the whole point. And then and I didn't put any parentheses with T's because that's superfluous at this point. Okay, next step. This is going to kind of seem out of nowhere. I know all this kind of seems out of nowhere. I got to remind myself where this goes here, and it goes here. Right, now what's the operator times its adjoint? 1. Yeah, it's 1, so I'm not changing anything. Okay. Okay, I managed to actually do that right. Okay. All right, what the hell is that? That, of course, is a time-evolving Hamiltonian in the Schrodinger picture. And this, of course, is a time-evolving operator. Time-evolving operator, whatever the hell it is. And now we got ourselves a time-evolving Hamiltonian. And they're permuted H, operator, operator H. Oh, and one subtracted from the other. What does that sound like? It's a commutator.
Oh, forgot to add.
I put a minus somewhere. That is that. That is called, actually it's not quite, I'm not done yet. I look like I'm done, but I'm not for a weird reason. Okay, let me work over to the left because it will save me precious seconds that I don't have. Okay, I'm not quite done yet. Why not? Because there's a simplification. And then we just need to look at it for a while and understand it. Where do I want to be? Okay. Note. Okay. Is this true? Does the Hamiltonian and the time evolution operator commute? And just in case you forgot, right, now remember, when I say parenthesis 0, I mean it's not special. In fact, it is the definition. It is not special. It's what we've been dealing with the whole time. Okay, is this true? Right, that's the unitary time evolution operator. Huh?
It should be correct.
It should be true. Does an operator commute with itself? AA minus AA? An operator, XX minus XX, that's going to be 0. What about a function of the operator and the operator? Okay, how about this? All right, we've actually covered this. Let's choose X because that's an easy. Okay, let's say f of X. Is that fine? X squared? That's easy, right? Right? Okay. If so, then what you have is X an operator and a function of same operator commute. Yeah, they're okay with that. Real easy. This is one that's like, your instincts hopefully would say, yeah, those commute. I hope your instincts would say that at this point. Especially with those e to the Hamiltonians just being e to the energy, right? Remember that part's actually like shockingly easy. And this is all really a facet of that same kind of mathematics. We're showing up. Okay, and that means that right? Because a commutator is the difference, and the difference is 0, therefore. So remember that you folks, I know I brought this up maybe too much, but one of the things you have to be careful about is when you have operators, you've got to be real careful about the order of operations. You can't be just changing it. Unless you know that you can, and this is how you know that you can. They commute. Okay, so therefore, and of course the adjoint well commute as well. But I'll just do this one. Okay, I have this situation here. So I'll do that. Which is, and again, this is not time involving, right? So let's go back over here. There's no time evolution. Right? If you look here, you can go back and look here and you can just wipe it out. You can do it that way. That's one way to think about it. Sorry, I'm kind of out of time, so I'm not explaining this super well. Okay. So that's true. Again, there's two ways to do this. One, just wipe it out here. This H, the Hamiltonian, the time evolving Hamiltonian is the same as the non-revolving time Hamiltonian. Nothing changes. For the reasons I just showed. Another way to do it is to use the equation that we just solved. The commutator of the Hamiltonian with itself. 0. So it doesn't evolve with time. That's what it means, right? The derivative, there's no t in it. So the derivative with respect to t gives you a 0. Right? So again, two ways to think of that. You can just wipe out these unitary operators and it's just h0, or you can just recognize that h of t is h0 for this reason. For this reason. It's two different reasons. The last thing I just want to say is, what is a Bisnocker about this is that this operator and this operator are the same. So like, let's say we're doing time evolution of the x. If this was just x not x0, see, it's x0, then it's just the letter x. And then this wouldn't be hard at all. But it's not, it's x of t. Now the thing is, if this was x at time 0, which is just x, I know what it is. And so then I would, it wouldn't be too hard to figure out the commutator. The problem is that I have one equation with not two unknowns, but the time derivative of the operator is equal to itself. It's a Diffie cube. If this was just x at time 0, I would just bring over dt and integrate it. It would be very trivial. But it's not. It's a Diffie cube. It's the operator. The derivative of the operator is a function of itself. And so we're going to run into some complexity, which of course there's always a slick, willy way to do it, and it won't be that bad. I've even already given you an example of how it's going to go. It's not going to be that bad. It's just not quite as straightforward as we would have liked. Okay, anyway, time evolution of plus and minuses in the handout I gave you, which we'll cover next time. So I guess I didn't need to run home. Sorry. No.